Welcome to Norton Chemistry. Today we're going to be doing an alkenes revision video. So alkenes are unsaturated hydrocarbons which contain carbon-carbon double bonds, and the general formula for an alkene is CnH2n. So for example, if you have an alkene with 2 carbons, which is ethene, it will have 4 hydrogen atoms. And the bonding in alkenes, so alkenes have sigma bonds, which are the carbon-carbon single bonds and the carbon-hydrogen bonds. And these form when there's an end-on overlap of S and S, or S and P, or P and P orbital between the plane of the carbon atoms. And then we also have carbon-carbon double bonds, which are made up of 1 sigma bond and 1 pi bond. And there are 4 electrons in the pi bond, making it an area of high localized electron density, which is important for the reactions of alkenes, because they can react with electrophiles which are attracted to areas of high electron density. And I'll come on to the definition of an electrophile later on. So pi bonds are the sideways overlap of p orbitals above and below the plane of the carbon atoms. So you can see here we've got a diagram of pi bond formation. So in this first diagram on the left, we've got a sigma bond between the plane of the carbon atoms. And then above and below the carbon atoms, we have p orbitals. And remember that p orbitals are dumbbell shaped. So if you were to add the bottom and the top p orbital together, you would get a dumbbell shape. And when the pi bond forms, we get a sideways overlap of the p orbitals. So you can see on the right, the pi bond is above and below the plane of the carbon atoms. And then that forms the carbon-carbon double bond. So stereoisomerism is a quite important topic for alkenes. And stereoisomers are compounds with the same structural formula, but a different arrangement of atoms in space. So this is different from structural isomers, which have the same molecular formula, but a different structural formula. So stereoisomers, the atoms actually arrange differently in space, because remember that molecules are 3D structures. EZ isomerism is a form of stereoisomerism where there is both restricted rotation about a double bond, because the double bond holds the atoms in place. This is why stereoisomers form, because the atoms on each side of the double bond cannot rotate around the carbon atoms, so they're fixed in position. And in EZ isomers, there's 2 different groups attached to each carbon atom in the double bond. So that means that ethene on the left, which has 2 of the same groups attached to each carbon atom in the double bond, cannot form EZ stereoisomers. And then if you look at this molecule on the right, you can see that it can form EZ stereoisomers because we have both the restricted rotation about the double bond, and we have 2 different groups attached to each carbon in the double bond. So on each we have a hydrogen and a methyl group. And CIP nomenclature. So we assign groups attached to the double bond priorities based on atomic number using the Cahn-Inglod-Prelog rule to name EZ isomers and also Cis-Trans Isomerism. What the Cahn-Inglod-Prelog rules say is that we must identify the atomic numbers of the first atoms attached to the carbon atoms in the double bond first. So for example, in this molecule on the left, we have on the left of the molecule, we have hydrogen attached, so that's the first atom, so that has an atomic number of 1, and a carbon attached, that has an atomic number of 12. So that automatically means that we must prioritize the methyl group on the left. And then on the right, the first atom attached on top is the carbon atom, which is 12, atomic number. And the chlorine on the bottom is the first atom attached, so that is 17, so that has higher priority. Then on the right, we have a slightly different molecule. So this molecule, I'll draw your attention to the bottom right. So we have CH2Cl. So the first 2 atoms on each group have the same priority, so they're both 12. But then we have the chlorine atom, which has an atomic number of 17, which is higher than the next atom attached to the methyl group, which is hydrogen, which is just 1. So we assign the highest priority to that CH2Cl group over the methyl group. So when we have the highest priority groups on different sides of the double bond, this is the E isomer. So for example, here we have E-butene. And when we have the highest priority groups on the same side of the double bond, that's the Z isomer. So you can see here we have Z-butene. And a helpful way of remembering this is Z-same-side. So when you have groups on the same side, you can remember Z-same-side is the Z isomer. So Cis-Trans Isomerism is a type of EZ isomerism, and the carbon atoms at each end of the double bond are attached to 2 different groups, but at least one of the groups attached to each carbon is identical. Here we have a cis isomer. So both carbons in the double bond have a hydrogen group attached, and they both have 2 different groups, and they both have restricted rotation about a double bond. So the cis isomer is when the same groups are on the same plane of the double bond. and the trans isomer is when they're on opposite sides. So addition reactions of alkenes, this is the main way that alkenes react, because they have this special carbon-carbon double bond, and the pi bond in the double bond is lower bond enthalpy than the sigma bond, so it breaks first, and that means that it can react by adding groups across the carbon-carbon double bond. So for example, we have electrophilic addition, which is an important reaction mechanism. I'm going to show you how to draw it. So we have ethene reacting with bromine. This is an important test for unsaturation, so the presence of a carbon-carbon double bond. And in this test, bromine water, which is usually orange, is decolorized. So we're going to start by drawing an ethene molecule and our bromine molecule. And because the double bond is our area of high electron density, it's going to induce a dipole in this bromine molecule. So usually this bromine molecule wouldn't have a dipole because bromine has equal electronegativity values. However, as one of the atoms becomes closer to the double bond, the molecule becomes polarized because the double bond is an area of high electron density. So the atom closest to the double bond will become delta positive, and the atom further away will become delta negative. So the electrons in the double bond from the pi bond are going to attack the delta positive bromine. And to show this, we draw a curly arrow, which shows the movement of a pair of electrons. And we draw us from the double bond directly to the bromine delta positive atom. And as these electrons attack the bromine, this will cause the bromine bond to break. So the electrons in the bond will attack the delta negative bromine atom. And then we move on to our next step. So the double bond is now broken. So we have a single carbon-carbon bond, and we have one atom with a bromine attached, and we have a positive carbocation. And we represent this with a positive charge on the carbon atom, which hasn't had an atom added to it yet. This bromide ion is going to be attracted to the positive carbocation, so the electrons in the lone pair are going to move to the positive carbocation, and we're going to draw that as a curly arrow. Make sure you draw it from the center of the lone pair to the carbocation, and then we're going to form 1,2-dibromoethane. And there's no additional side products because it's an addition reaction. So Markovnikov's rule, this is an important rule for determining which products are most likely to form in electrophilic addition. And major and minor products form when an unsymmetrical alkene reacts to form structural isomers. The major product will form from the most stable carbocation intermediate, which has the most alkyl groups attached. So for example, we have a primary, so that's the one with the O next to it, carbocation. We have a secondary carbocation, which has 2 alkyl groups attached, and a tertiary, which has 3 alkyl groups attached. And out of these 3 types of carbocation, the tertiary will be the most stable, because each alkyl group donates and pushes electrons towards the carbocation, which increases its stability. So for example, in this reaction here, we have butanene reacting with hydrogen bromide, and it has to be hydrogen bromide, because if it was bromine, then we wouldn't have structural isomers forming. So we form a secondary carbocation and a primary carbocation. And the secondary carbocation, which is where the bromine attaches to the second carbon atom in the chain, so 2-bromobutane, is the major product, and 1-bromobutane is the minor product, because secondary carbocation is more stable because it has more alkyl groups attached to that carbocation. We've got some other important addition reactions. So we've got hydrogenation, and in the presence of nickel catalyst, alkenes undergo addition reactions with hydrogen to form alkanes. You can see the equation there, and as you'll see, we don't form any waste product. In the presence of sulfuric acid catalyst, alkenes react with steam, which is gaseous water, to form alcohols. So we need to have that acid catalyst, and it can be phosphoric acid as well, and the water must be gaseous for the reaction to take place. And this is an important way of forming alcohols in industry. And as you'll see again, we don't form any waste products because it's an addition reaction. Addition polymers are important unreactive macromolecules made from small repeating units, which are monomers, and form these from alkenes when the double bond breaks and we add 2 groups across each side of the double bond. And when you're drawing addition polymers, I recommend that you always draw them like ethene. So you always have 2 carbons as a repeat unit, and then any other groups are either above or below the carbon atoms. And you must include the long side links with the brackets because the side bonds show that the repeating unit is repeating many times over. And it's important to know how we can dispose of polymers. So we can do combustion for energy production, and then we can also remove toxic waste products, for example, hydrochloric acid, which would be formed from this polychloroethene. And we can also use polymers as an organic feedstock for the production of new polymers. We've got an exam question. Two reactions of compound C are shown in the flowchart below. So we've got compound C, which is dichloroethene, reacting to form an alcohol and a haloalkane. So for reaction 1, we're gaining an alcohol group. So that's going to need gaseous water or steam and sulfuric acid catalyst. In reaction 2, compound C reacts with bromine to form compound D. Give the systematic name of compound D. So if we have a look at compound D, we can immediately see it's got 2 carbon atoms, so we can write ethane. And then you'll notice that we have a bromine at carbon 1 and carbon 2. We're saying this is carbon 1 and this is carbon 2 because we need to number for the lowest possible numbers in our name. And then bromine comes before chlorine in the alphabet. So chlorine is going to give a chloro prefix and bromine is going to give a bromo prefix. So we need to put bromine first. So it's going to be 1,2-dibromo. So it's important you say dibromo because there's 2 bromine groups. And then it's going to be 1,1-dichloroethane. And then we're being asked to outline the mechanism for reaction 2, include curly arrows, charges, and relevant dipoles. So they tell you exactly what you need to include in your mechanism. So we're going to start with our dichloroethene, and we're going to draw a bromine molecule with its dipole. And the electrons from the double bond are going to attack the delta positive bromine, which is the electrophile. And that's going to break this bromine bond. So the electrons go to this delta negative bromine atom. That's going to form a single carbon bond with bromine at either position because they're both primary carbocations. And we're going to have our bromide arm with a lone pair of electrons and a negative charge. I'm going to draw our curly arrow from the center of the lone pair of electrons to the carbocation. And that's going to form our final product, which is 1,2-dibromo 1,1-dichloroethane. Thanks for watching. Make sure to check out my revision video on alkanes, which will be in the bottom right hand corner now. You can also check out my website to purchase my notes and flashcards. The link will be in the description below.